This person has a mustache. This person does not. All these people have a mustache. But this person does not. Or actually does. We used a pre-trained AI model and gave it 10,000 images of celebrities, such that the final model is able to classify whether or not a person has a mustache with over 90% accuracy. And this model is very sure that this image has a mustache. So how does that work? We started with the popular ResNet-50 model, a convolutional neural network. We used it because it's great for image classification and because we could easily use it in our project due to the model already being implemented in the Python library called PyTorch.
The model was initialized with pre-trained ImageNet 1K v2 weights, and after that we needed to train the model for our specific task, so we needed pictures from people with and without mustaches. We turned to CelebA dataset, which has over 200,000 labeled images. From these images we used 5,000 with and 5,000 without mustache. Doing this alters the weights within the model itself to, instead of recognizing the difference between a boat and a dog, to recognize whether Gordon Ramsay has a mustache or not.
Now we can throw any image into the model and it will tell with a given certainty if a person has a mustache or not.
However, going back to the beginning, why did the model think this picture had a mustache even though both you and me can clearly see it doesn't? This is because we performed an adversarial attack on the model. As an attack, we used the Basic Iterative Method, also known as BIM, which uses the fast gradient sign method iteratively. This method focuses on maximizing the loss to find the weak points in how the model recognizes a mustache. This information is used to alter images ever so slightly, such that the human eye would barely notice the difference. However, the AI model would see something else entirely and misjudge the presence of a mustache.
Such an image is called an adversarial image and results in a successful attack. To defend against this attack, two solutions are suggested. The most obvious trick is to defend against the adversarial attack by retraining the model again, also using the adversarial images in its training set. This way, the model learns from its own mistakes by diminishing weights and biases for pixels that do not correlate to the mustache. Another method to defend the model against an adversarial attack
is to introduce a noise layer at the start of the model. By applying noise to the input image during training, the model must look at relatively more generic features rather than an individual pixel value. During inference, the pixel-wise perturbations of an adversarial attack are blurred out by adding the noise. Using adversarial training ensures the model is able to properly classify the images generated from the original adversarial attack.
However, when a new attack is performed on the resulting model, the attack still works. The noise layer by itself also does not change much, as the original adversarial attack still works on 2 out of 4 cases, and a new attack works in 3 out of 4 cases. Combining the two defenses, the resulting model is able to properly classify all images from the initial attack, and when a new attack is performed on the model, only in 2 out of the 4 images the attack fools the model, and the model is less certain about the people having a mustache.